let's put some of this association knowledge of ours to work. As always, we start with an example, and this time we're comparing mean reaction time using red and green targets. This is just simply a target that comes up on the screen, and you click as quickly as possible using your mouse, which is the correct color. Now we have two data sets. One is the unpaired, so this is data statement in SAS to name the data set, the input for defining the variables, color and reaction time. Here is your data. In the paired data set, we have the same thing. However, because it's paired, we are going to be doing what's called a wide format, which is your data is going to be in columns. So you're going to have your reaction time for green, your reaction time for red, and then we're going to calculate the difference between the reaction times, which is simply just taking the difference between the columns. Now, just a little note, we cannot calculate paired differences in the unpaired data set, of course, because the data is not paired. Okay, let's start with some summary statistics. Using SAS and proc means, we're going to call the unpaired data set. And by color, we're going to analyze the reaction time variable and produce the mean, the variance, the standard deviation, the standard error. And what this is, max decimal, is just how many decimal points we want in our answer. Now, in the output, we can see immediately green, red. Here's your mean. Here's your variance, your standard deviation, and your standard error. You can see that the difference between the means, there is one. Doesn't seem huge, but there's definitely a difference. In terms of variance and standard deviation and standard error, they definitely seem rather close. So whenever anyone says rather close, the knee-jerk reaction is, what do you mean by rather close? And is that statistically significant? And this is just because we've been trained to react that way, right, in medical research. And it makes sense. It's for a reason, right? So let's do that. I mean, thanks to Gossett and the student's t-test, we're going to be able to tell whether or not the reaction time between the two colors, so red and green, the difference we observed is significantly different. And so we use proc t-test in SAS. Here we're calling the same data set unpaired, where the class, which is color, is telling SAS that we want to compare the levels within color. There's only two in this case, which is red and green. And the variable is reaction time. Now, there's a lot to talk about in this output, but what we're going to do is just kind of point out the few things that we'd like to start with. So one is, let's just look here. When you look at the difference, the mean difference is 8.48. And the question, of course, is if they were not different, so then we fail to reject the null hypothesis, it means that the difference would actually be 0, correct? And so the question is 8.48 significantly different from 0? And right away you see in the 95% confidence interval that it contains 0. So that should be your first red flag. Whoop, wait a minute. Now, if you keep looking down, we look at this famous p-value, which don't worry, we're going to talk a lot about this in this course. If you look at the p-value, it is 0.5323, not 0.05, no, but 0.5. So clearly it is greater than 0.05. And this makes sense because if your confidence interval contains 0, which is your null hypothesis, it makes sense that your p-value is going to be greater than 0.05. Now, if we just look up here in this last little red box that I've added, just look at the standard error here. It's basically 13. And all I want you to do is remember this number for when we do the same analysis, but with the paired data set. All right, now this is just a refresher because we've already kind of talked about this. This is the student t-test to compare two unpaired independent means. Here's your student t ratio. You'll remember that this is the difference In this case, we're using the example that we've used previously about the diastolic blood pressure. This is the difference between your two means. This is your null hypothesis, which is the difference between the hypothesized population means, which in this case is going to be 0. Here is your pooled standard, your pooled variance, which is going to lead to your standard error. This is the equation for your pooled variance. And this here, remember I talked about degrees of freedom. We'll talk about that, along through the course as well. But all this is telling you is how to calculate the degrees of freedom when you have two means that you're comparing. In this case, you take the sample size of the one group minus 1 and the sample size from the other group minus 1. And there's your degrees of freedom. You add them together and there's your degrees of freedom. Now in this slide, all we're doing is we're actually performing the calculations for you, and you can go back to the previous slide and you can verify that what SAS gave us from the proc t-test is the same as what we've calculated by hand. If you'll remember correctly, I said remember the standard error of difference for when we go to the paired analysis, and it was, and I said basically 13. So this is exactly what SAS found. Once again, the student t-test exactly the same, of a value of 0.65 and with a p-value of 0.532. If you remember correctly, this is exactly what SAS gave us. So have a peek, go back and have a check just to make sure we're not lying to you. No, I'm kidding. We wouldn't do that. Now remember I said that we were going to repeat the same analysis but using the paired data set. So this is what we're doing here. We're using proc means, so same thing, but we're calling the paired data set this time. We're asking for the same summary statistics. We don't have to use the by color statement because now the data is in columns. So we just specify the columns or the variables. So you have the reaction time for green, reaction time for red, and the difference. Remember we calculated the difference per pair. And so what it's going to give you down here in the output is going to be by variable. It's going to give you your mean, your variance, your standard deviation, your standard error, your t-value, and your p-value. What's that? Okay. So what means the means procedure does for you if you ask for it is very simply for each variable, it's going to look at this mean and it's going to say, okay, let's test it to see if this mean is significantly different from 0. So that's just something it does by default if you ask for the t-value to be performed, which we did up here, right? The t and the probability of t. And in this case, of course, 234, is definitely significantly different from 0. 226, of course. 848, well, actually, it's only just significantly different from 0, but it's still significantly different from 0. So keep that in mind. Okay, of course, we have to repeat the t-test, but this time using the paired data set. So this is what we're doing here. Proc t-test. You guys are getting good at this. The data we're calling the data set paired, but now we're saying, don't forget when we're doing this data set that these two variables are paired, meaning that you have to consider the pairing by row, actually, is the way SAS does it. So here's your two variables, reaction time for green, reaction time for red. Here's the output. Let's start as we did last time. Let's look right away at the confidence limits. And look at that. The confidence limit, or the confidence interval, does not contain 0. So you'll think, okay, well, when it did contain 0 for a difference, our null hypothesis is 0, so our p-value should be greater than 0.05. In this case, it does not contain 0, so my p-value should be less than 0.05. Let's have a look. Look at that. It is. It is less than 0.05. Interesting. Now let's look up here at the mean. So this is the mean difference. Here's the standard error. Okay, and you remember from the unpaired analysis, your standard error was about 13. And here, just to confirm our equations on the t-value, remember the t-value is going to be the difference divided by the standard error, and this is equal to 2.8. If we look down here for the t-value, there it is, 2.8. So you must be thinking, well, that's kind of odd. If I treat the data as unpaired, I do not find a statistically significant difference. However, using the same data, but treating it as paired, I do find a significant difference. That's a bit odd. Okay, so let's try and explain this. The first thing we're going to do is we're going to look at the association between the reaction time for green and the reaction time for red. How are we going to do this? Well, you guys are experts. We now are going to use the Pearson Correlation. Perfect. So in SAS, that is the proc-core procedure, okay? And using the two variables, we are going to send them in for a Pearson Correlation coefficient analysis. What it does immediately is it gives you your simple summary statistics. We already have those. Perfect. But then when we look at the output here for Pearson Correlation coefficient for reaction time green versus reaction time red, the R value is 0.9478. Now you'll remember that we stated that a perfect correlation was 1 or -1 depending on the direction. The p-value on this is statistically significant with 0.0142. So this means that there is a positive, strong correlation between reaction time of green and reaction time of red. All right, this is a busy slide, granted, and I'm going to walk you through it. So don't worry, just sit back, listen up. Easy stuff here. So we're talking about comparing two reaction times, one to green, one to red, and we want to know if the mean reaction time of both of those colors is significantly different from each other. If it's not, then it's basically no different than 0. Okay, cool. We now find out, whoops, there is a strong correlation between these reaction times. And when we do the t-test, whether it's unpaired or paired, we show a difference, a big difference between the interpretations. Okay, so this is where we're at. Now, you'll remember that the pooled variance, this is the equation for the pooled variance here. And if we calculate it, it's 422, fine. And if we were to then incorporate this pooled variance into our equation for the variance of the difference, which is what we're interested in, here and here, which is also like this, which is what we've given in your previous slides, it's going to be 422, right, over n plus 422 over n, or 2 times 422 over n, which is 5. If you do that, the value is 168,875. If you take the square root of 168,875, you're going to find it's 12.99, which is 13. Remember I asked you, in the unpaired analysis, remember the standard error, it's 13. Well, that would be this value right here. The standard error of the difference would be 13 for unpaired. Now, what would you say if I were to tell you that in the variance of the difference, if your variables are correlated, so they do have, there is a relationship between them, that we should adjust for that because they're correlated, and you do so here in this part of the equation. So this is just an adjustment for the correlation, but you'll see an important piece here, R. What's that? That's the Pearson correlation coefficient. So this makes sense. If there is no correlation between the two of them, 0, literally 0, then this whole term goes away. And if that's the case, 13, right? For the unpaired data, we are assuming R is 0, then the standard error ends up being 13, which is the square root of 168. But we found, oh, no, that's not the case. There's actually 0.9. Whoa, there's a very strong relationship. So if we do, and we add on this calculation, then it's 168,875 minus what this term is, which is 159,721, and we get 9.154. If we then, so this is the variance of the difference. If we then take the square root for the standard error, we now get what we found in the paired analysis, which is 3.0256. And then when you do your student t, we get exactly what we got in the previous slide. Interesting. So if we look at this graphically, so this is the relation between reaction time and target color. So meaning that by target color, we're going to compare the means of the reaction time. So what we have here is the reaction time to the red targets on the x-axis and to the green targets on the y-axis. Now you can imagine you could do it either way. It doesn't matter where is green and where is red. The Pearson correlation coefficient we found was high, 0.95. And there you go. Obviously here it's very clearly indicated by this line between the data that there is a strong linear relationship, and in this case positive linear relationship, between the two target colors. And the piece that you need to remember is that if there is a strong correlation between the variables or the groups, sorry, the data that you are analyzing in a t-test, for instance, you have to take that into consideration because it's something you know. And if it's something you know, you can account for more of the error or the unknown variability. And when you do so, you reduce the error, and by doing so, you get a better estimate of your test from your test, which is in this case, you're testing to see if there's a significant difference between the two. There's the story for you. So keep that in mind when you're working with your data, and if there's the possibility it's correlated, you must account for it. Okay, the next few slides is a bit of a brain teaser. So it's just to kind of strengthen your knowledge about what we've covered so far in this lecture. So here are two examples of incorrect p-values in the comparison of two means. So the student t-test for comparing two independent sample means involves pooling two variances, and we saw that in the previous slides. If the difference in size of the two variances is large and the sample sizes are different, the probability of getting a biased p-value estimate increases. So this is just something you need to remember and something you should look for when you're doing even just simple t-tests is, are the variances equal or similar? And do I have an unbalanced analysis? So meaning that the two group sizes are very different. Okay, as always, let's look at an example. So in this case, the group with larger n, or sample size, also has larger variance. And so that incorrectly pooling the variances produces a larger p-value. And we're going to show this. So once again, here's our data statement. We're creating a data set called T1. It's once again diastolic blood pressure. We have a group 1 and 0 and 1. We run our proc means to get summary statistics. We do it by group. As you can see in the output, here's your group 0, here's your group 1. Your mean is 11 and 5, so they're clearly different. The standard deviation and the variance. So we're looking at the variance, and whoa, that's a big difference. 4889 versus 2.5. That's a big difference. In terms of the sample size, yeah, it's that's a big difference too. It's twice as big in one of the groups. Okay, so what's that going to lead? Okay, let's get on with the t-test. So proc t-test, we're calling T1 our data set. The grouping variable it's called group, very appropriate. 2 levels, 0 and 1. The variable of interest is diastolic blood pressure. Here's the output. Okay, let's zero in right on the p-value to begin with. So the pooled variance p-value, so meaning the t-test that used the pooled variance, which we've been showing you all along, not significant. Oh, that means we have to, increase the sample size, or we have to redo the experiment. No. Don't worry. If you look below, the Satterthwaite method, which is a different way of calculating the variance, it is significant. Oh, well, that's better, because that's what I expected, considering the difference in the means was huge, right? 6. So what's going on here? Well, it's what we warned you, that if you used the pooled variance technique when the variance between the two groups is very different, it's not appropriate because of bias. And this is even worse when the sample size between the two groups is also very different. And so SAS knows this. Everybody who's been in the world of statistics for a while knows to be to look for this. And so the way SAS does this is it tests the equality of variances between the groups. And you'll see here, using the folded F, which is the method, the folded F, we'll talk about a little bit later, this p-value is significant. So that means that there is a significant difference in variance between the two groups. In this case, when there is inequality of variances, the pooled method is not valid. It introduces bias. And in that case, you should consider the Satterthwaite method, where it is more robust and allows for inequality of the variances. And this is the p-value that you would report. All right, let's do this again, but this time the group with the larger sample size, just like last time, has the smaller variance. Last time it had the larger variance. And in this case, once again, incorrectly pooling the variances will produce a smaller p-value. Okay, here's the data. Same deal, except for the data's changed a little bit in order for us to switch the variance around. Proc means, here's the results. Your mean value, very different, so we expect a significant difference, sorry. The sample size, whoops, yeah, definitely, twice as big, but this time, the group with the larger sample size has the smaller variance, and that's a 10-fold difference in variance. Wow. Once again, we perform the t-test. No big surprise here in the code, but when we look at the p-values, the pooled variance gives you statistical significance. However, when you look at the Satterthwaite method, it's not significant. And if you look at the equality of variances, it's saying, it is not, the variances are not equal, because the p-value is significant here, meaning that you reject the null hypothesis of equality between the variances. So this is the trickier situation or scenario. The reason being is that as a researcher, when you see this, you go, oh my God, that's amazing. I found statistical significance in the difference. Perfect. Publish. Unfortunately, you can't do that, because it would be inappropriate because of this. You have inequality of the variances between the groups, and therefore you must consider the Satterthwaite method. Okay? And unfortunately, this is a very common mistake that people will look at it and go, oh, that's a problem. In the previous one, you're going to find no significance. You can look at Satterthwaite, significant, and you go, oh, okay, what's that? Quick, let's check it out. Oh, phew, that's amazing. Look at the equality of variances. We reject that, so we reject the null, and therefore we're good. And so that in that case, you're okay. But in this case, you're not okay, because you should not accept the pooled p-value because it's inappropriate, and unfortunately, you're going to have to go with the I did not find a statistical significance between the groups. Unfortunate. Now you might be thinking, hey, could I just always use a Satterweight? And yes, you could. Actually, you could. If you were to use Satterweight all the time, you would always get a correct p-value. However, when your variances are equal, the Satterweight tends to give a little, just a pinch more of a conservative p-value if you were to do, thousands and thousands and thousands of tests. So that's the reason why that there is the choice that you obviously want to get the best estimate possible whenever you do a test. And so if you know that the variances are equal, then you should be using the pooled variance technique. And if they're not equal, then you just use the Satterweight. And that's it for lecture 3. Next up will be part 2, lecture 1, and we will talk about the statistical model.